Very often in mathematics we're interested in the negation of a first order formula. So if you have a first order formula f, then the negation of f is just not f, like this. This happens very often in analysis where, for example, things like continuity or differentiability or tending to a limit are expressed as quantified statements, which are interpretations of first order formulas. So it's useful to us to have logical equivalents for the negations of first order formulas which begin with quantifiers. And thanks to the logical equivalences we learned in the last video, we're able to actually shed some light on what the negation of these statements really means. So the two logical equivalences I'm talking about are, first of all, that the negation of for all x p of x is logically equivalent to there exists x not p of x, and the negation of exists x p of x is logically equivalent to for all x not p of x. So let's see this in some specific examples. We're going to look at the definition of boundedness of a function. So perhaps you've come across this in your analysis course, and perhaps not, but if you haven't, I'm just going to remind you of the definition. So a function f, and I'm thinking of a function from the real numbers to the real numbers, is bounded if and only if there exists a real number m, such that for every real number x, the absolute value of f of x is less than or equal to m. And that is an interpretation of a first order formula. So this is an interpretation of a first order formula, specifically this first order formula over here. Exists m for all x p of xm. So if you interpret that formula by saying the domain is the real numbers and the relation p of xm is absolute value of f of x less than or equal to m, then you get the definition of boundedness. So if we want to know what it means for a function not to be bounded, we can look at the negation of this first order formula. And if we subject the negation of that first order formula to the same interpretation, we'll get the definition of a function not being bounded. So of course you can just stick the word not in front of this to get a statement of what it means for a function not to be bounded, but hopefully the logical equivalences that we learned will actually give a more insightful and easier to understand definition for a function not to be bounded. So let's try doing the negation of this first order formula. So the negation of there exists m for all x p x m would be logically equivalent to, according to the logical equivalence for not there exists that we learned at the end of our last video, for all m not for all x p of x m. Okay, now we have a formula where we've got not in front of for all, so we can use the other logical equivalence that I put on the last slide. We now get for all m exists x not p of x m. So that lets us rewrite the definition of not boundedness in an interesting way. So a function f is not bounded if and only if for all m in R. So I'm interpreting this formula we just worked out in the same interpretation as we use for the definition of boundedness. There exists a real number x such that it's not the case that absolute value of f of x is less than or equal to m. And of course we could actually express the last bit of this formula in a slightly simpler way. So this bit here could be re-expressed as saying, well, if it's not true that the absolute value of f of x is less than or equal to m, then actually the absolute value of f of x must be greater than m. So we could simply say absolute value of f of x is greater than m. And that gives a relatively simple description of what it means for a function not to be bounded. It means that for every m, a real number, there exists a real number x such that the absolute value of f of x is greater than m. And the real advantage to this method is that when we were working out what it meant for a function not to be bounded, we actually didn't have to think about analysis at all. So there was no problem with getting bogged down by details about the specific meaning of terms from analysis, because we were able to do this calculation here just thinking about logical equivalences and not using any of our knowledge of analysis. So that's often really helpful, because when you're doing purely logical operations on a statement, you don't have to be confused by the specific thing that you're talking about, the specific area of mathematics that you're actually working with. So we've managed to negate the definition of boundedness. Let's look at something which is a bit like the definition of continuity, but not quite the definition of continuity. So what I'm going to do is I'm going to explain why there's a there seems to be a problem with applying what we've learned to definitions of things like continuity. And then I'm just going to do an example of negating something which is related to continuity, but not quite continuity. So the problem with talking about the definition of continuity as an interpretation of a first-order formula is this. So the definition of continuity usually looks something like this. It will say, for all, so we're talking about continuity at a particular point x, and the definition will say something like this. For all epsilon greater than 0, there exists a delta greater than 0, such that for all y in R, and then it will go on to have a bunch of other stuff which I don't care about right now. But here's the problem that seems to exist with this definition. When we did an interpretation of a first order formula, we chose a domain for that interpretation, and all of the variables had to come from that domain. But it seems as if that's not what's going on in this definition, because it seems like we've got some variables y, or some variable specifically y, which can be any real number, but on the other hand we've got other variables, epsilon and delta, which have to be a positive real number. So you might think that this is a real problem for us, because, as I said, in our interpretations, all of the variables are supposed to belong to the same set. But we can actually get around this at the cost of making the formula a bit more complicated. And the way in which you can get around this, so the way in which you can see the definition of continuity as genuinely being an interpretation of a first order formula, is to, instead of writing it in the normal way, you could write something like, for all epsilon greater than 0, come on, that's not it. So for all epsilon in R, if epsilon is greater than 0, then something happens. You can write if and then with an implies symbol. So at the cost of making your formula loads more complicated, you really can interpret definitions like the definition of continuity as interpretations of first order formulas. But actually what you find is that it doesn't really make a lot of difference when you do this, and you can actually negate first order formulas just by forgetting about this issue completely. Anyway, that said, let's look at a related formula and try and negate it. So all I'm going to do as another example of negating first order formulas is to look at this first order formula here and to try and find a simplified logical equivalence to this thing. So before I do that, I want to remember a definition, a useful definition, or rather a useful logical equivalence to do with implies. So you'll probably remember that we actually studied how to negate implications when we learned about propositional calculus. So we looked at what would it mean, what kind of logical equivalences there are for implication statements. So we knew that phi implies psi was logically equivalent to, how did we do this? This was phi or not psi. So if you have trouble remembering this, then the easy way to remember it, as I think I might have already said, is to think, when is an implication false? There's only one way for an implication like this to be false, and that's when phi is true and psi is false. And the only way for this or statement to be false is for psi to be false and for phi to be true. So this looks correct to me. Hopefully I've got this right. Okay, so from this we can get the negation of phi implies psi, because that's going to be logically equivalent to the negation of psi or not phi, which by De Morgan's laws is logically equivalent to not psi or and not phi, which is of course just not psi and phi. Okay, so if we want to negate this first order formula, let's do it. We have negation of for all epsilon exists delta for all y, p of y delta implies q of y epsilon. And we're going to use the same quantifier trick or quantifier logical equivalence that we've used before to say that this is logically equivalent to there exists epsilon such that not there exists delta for all y. And just going to be a bit lazy here and write p implies q rather than p of y delta implies q of y epsilon. Of course, that's logically equivalent using our negation trick again to exists epsilon for all delta, not for all y, p implies q. Okay, and we can do it again. We've got not for all, and we know that that is the same as there exists not. So we have exists epsilon for all delta, there exists y, such that not p implies q. And finally, we know this logical equivalence for the negation of an implication. So we get exists epsilon for all delta, exists y, and then finally we will have not q and p. Okay, so we've made it. We've managed to negate this very complicated statement. When you get fluent at doing this, you start to realize that all that's going on here is when you want to negate a quantified statement like this, all you have to do is flip the quantifier, so change a for all to there exists, and change an exist to a for all, and then move the not one step further on. And it becomes really easy to negate these formulas, even when they're incredibly complicated and difficult to look at. So this is really the power of first order logic, and the power of using these abstract first order formulas is they allow us to find the negation of very complicated statements indeed, just by this kind of algebraic method, which means we can forget about what the formula actually means in its interpretation and just focus on manipulating the symbols involved. That kind of abstraction gives us a really powerful tool which we can apply in all kinds of areas of mathematics.